All right, welcome to Gradient Daily. Today, we're jumping into a paper that honestly takes a sledgehammer to one of the core ideas in 3D reconstruction. The paper is called Pi³ Permutation-Equivalent Visual Geometry Learning, and it comes from a brilliant team over at Shanghai AI Lab, ZJU, and SII. This one is a game changer, so let's get into it.
So, to really get why this paper is so important, we've got to start with a big question. What's the Achilles heel of modern 3D reconstruction? I mean, what's that one thing that can bring even the most sophisticated, state-of-the-art models to their knees? And this graph right here, this is the problem in a nutshell. It's basically a performance lottery. Look at that jagged blue line. That's a top-tier model, VGT, running on the exact same set of images. The only thing that's different is which image it's told to start with, the reference view. And look at the results. They're all over the place. Pick a good starting frame, you get low error. Pick a bad one, and your performance just tanks. It's totally unpredictable. Now, see that flat, calm red line at the bottom? That's Pi³, rock solid. No matter where it starts, the performance is the same. That's not a lottery, that's reliability.
Okay, so let's dig into this. The authors call this critical weakness the reference view bottleneck. Think of it like this. You're building a house of cards, and the stability of the entire structure depends entirely on the very first card you place. That's what's been happening in 3D vision. We've inherited this old idea that you have to pick one image to be your anchor, your frame zero, and then everything else is built relative to that single point of view. But as we just saw in that graph, picking the wrong first card can cause the whole thing to come crashing down.
And the authors are pretty blunt about it. They basically say, hey, this whole reference view thing, it's not a feature. It's a bug. They call it an unnecessary inductive bias, which is a fancy way of saying it's a built-in assumption that's actually hurting us. It's this old habit we've carried over from classical computer vision, and it's fundamentally holding back our modern, powerful networks. It's like putting a governor on a sports car engine. It just doesn't belong there anymore.
So, if the reference view is the problem, what's the solution? Well, this is where the paper gets really elegant. The authors propose something that sounds almost too simple to be true. They ask, what if we just get rid of it? What if we build a model that doesn't pick a reference view at all? Not first, not ever.
This is the perfect way to think about it. The old way was a dictatorship. One image, the reference view, was the king. It decided the laws of the 3D world, the entire coordinate system, and every other image had to fall in line. Pi³ is a complete paradigm shift. It's a democracy. Every single image gets an equal vote. There's no king, no special treatment. All views are treated as peers, and they work together to figure out the scene. It's a total flattening of the hierarchy.
Okay, that all sounds great, right? A democracy of images. But how on earth do you actually build a neural network that thinks that way? How do you feed it a jumbled up pile of photos and have it spit out a perfect 3D model? Well, the how is where the magic really happens, and it's all thanks to a really cool mathematical property.
And that property is called permutation-equivariance. It's a bit of a mouthful, but the concept is super simple. Order doesn't matter. That's it. If you shuffle the input images, the output predictions for those images get shuffled in exactly the same way, but the actual 3D reconstruction, the geometry, the camera poses, it remains absolutely identical. It means the model has learned the relationships between the images, not their position in a sequence.
So how did they bake this into the architecture? Well, they basically had to go in and remove anything, and I mean anything that could give the model a clue about the order of the images. First, they ripped out things like positional embeddings, which literally tell the model, you are image number 1, you are image number 2, gone. Second, they got rid of any special tokens that other models use to say, hey, this one's the reference view. Nope, not here. Third, they use a transformer architecture where attention mechanisms let every image talk to every other image symmetrically. And finally, and this is key, they train the whole thing on relative relationships. The model doesn't learn camera A is at coordinate x, y, z. It learns camera A is this far from and oriented like this relative to camera B.
And this just lays it out perfectly, doesn't it? On one side, you've got the old guard, totally dependent on a fixed reference, super sensitive to the input order. On the other side, you have Pi³, no reference needed, treats all views the same, and it's completely order invariant by its very design. It's not a tweak, it's a whole new philosophy built into the model's DNA. All right, so the theory is beautiful, the architecture is clever, but does it actually work? Talk is cheap. It's time to see the receipts. Let's get into the results and see how Pi³ stacks up against the competition. First up, camera pose estimation. Now, the number you really want to look at here is for real estate 10K. This is an in-the-wild dataset, a real torture test, and the model has never seen it before.
we're looking at AUC, where bigger is better. The previous champ, VGT, gets a 77.6. Not bad, but look at Pi³, 85.9. That's not just a little better, that's a massive jump of over 8 points. This thing generalizes like crazy.
Okay, now let's talk about how accurate the camera path is. Here, we're looking at absolute trajectory error, so lower is better. Check out the Sintel benchmark. VGGT has an error of 0.167. Pi³³ comes in at 0.074. I mean, do the math. It literally cuts the error in half. More than half, actually. That is a gigantic improvement in accuracy. And the winning streak continues with video depth estimation. Again, lower is better here. Across 3 different really important benchmarks, Sintel, Bon, and the famous Kitty dataset for autonomous driving, it's just a clean sweep. Pi³ beats the previous state-of-the-art on every single one. It's not just good at one thing, it's just better. Period.
And here's the kicker. You'd think with all this extra accuracy, there must be a catch, right? It's got to be slower. Nope. It's actually incredibly fast. We're talking 57.4 frames per second on Kitty. That's not only faster than its main competitor, VGGT, it's almost 50 times faster than another big model, Duster. So you get state-of-the-art accuracy and blazing speed. There's no trade-off.
But honestly, for me, this is the most important slide in the whole deck. This is the smoking gun. This table shows the standard deviation, the wobble in performance when you just shuffle the input images. Look at VGGD's numbers, 0.033, 0.009. Now look at Pi³. It's an order of magnitude lower on DTU, and on E3D, it's practically 0. This is the proof. This is what it looks like when you end the performance lottery. The model's rock-solid stable.
And, okay, enough numbers. Let's just look at the results. The pictures speak for themselves, right? These are point clouds built from really tricky real-world videos. You've got this dense, complex cityscape on one side and a huge, sprawling canyon on the other. The reconstructions are just so clean and complete. The level of detail is just incredible.
And it's not just static scenes. Look at this. It handles dynamic motion beautifully. You've got someone doing parkour, go-karts racing around a track. These are notoriously hard scenes to reconstruct because everything is moving, but the model produces this really coherent geometry without all the weird floating artifacts and broken pieces you usually see with this kind of footage.
Okay, this all looks amazing, but you know the drill. No paper is perfect. So let's take a step back, put our critical thinking caps on, and talk about the strengths but also the potential limitations and where this research could go from here.
So the strengths are pretty clear, right? First and foremost, its robustness is off the charts. It completely solves that input order lottery problem. It sets new SOTA records for accuracy on a whole bunch of important benchmarks. It's super fast, and it generalizes incredibly well to data it's never seen before. It really is a landmark paper.
But it's also important to understand the context. This amazing performance is fueled by a massive training data set. They combined 15 different data sets, which is a huge undertaking. And, you know, it's still a vision model. It's probably going to struggle with the usual suspects. Big, textureless white walls, shiny reflective surfaces, things like that. A great next step would be to really torture test it on some extreme cases, like videos with very few overlapping frames, and see where it breaks.
Okay, let's wrap this up. We've gone through the problem, the brilliant solution, and the incredible results. So what's the bottom line? What are the 3 key things you absolutely need to remember from this? All right, here's your 30-second takeaway. Number 1, the reference view is a bug, not a feature. We now have proof that relying on one is a source of major instability. Number 2, permutation-equivariance is the answer. Treating all views as equals, this democracy of images, is what unlocks this new level of robustness and accuracy. And number 3, and this is the big one, this reliability is what makes this tech ready for the real world. For things like robotics, AR, and autonomous cars, you can't have a performance lottery. You need something this trustworthy.
And that really leaves us with a fascinating question to chew on, doesn't it? This paper found a fundamental, unnecessary bias that everyone just took for granted, and they eliminated it. So it makes you wonder, what's the next reference view? What's another core assumption that we've baked into our models that's secretly holding us back? Food for thought. Anyway, that's all for today on Gradient Daily. Thanks for diving in with us. If you enjoyed this, definitely hit that like button and subscribe, and we'll see you back here tomorrow for another deep dive into a great paper.